As part of today, for people that aren't aware, we're having a special day in the conference in honor of Professors Narasimhan and Seshadri, who both passed away in the last year. And as part of that, I'm very happy to welcome back Jacques Hurtubise for his third talk in his lecture series. Please go ahead.
Okay, well, it's a very great honor and pleasure to give a talk in this day in memory of Narasimhan and Seshadri. It was always a great pleasure to meet them in my various visits to India over the years, and you know, to both as a sort of direct link with the history of our subject, and also to see them so, you know, continuously alive and interested in what was going on at the time. In particular, they held a really very nice meeting, which was the 50th anniversary of their paper in the Annals on bundles on a Riemann surface, and so it was held in Chennai. And they both of them were there, and it was you know, astounding to see them really on top of everything that was being discussed in the talks, and so the memories are very fond. And well, I just hope that today's lecture is a sort of small tribute to their work. We were talking the last week about various integrable systems, notably the Hitchin system, that were basically gave you an integrable system of, well, in the case we were studying, of Jacobians. And the sort of theme of the second lecture last week was to show that the symplectic geometry of this system was tightly linked to the just the canonical bundle of the curve, the Riemann surface X, over which these things live. So that just to so I was going to recall a few of the systems we discussed, and but the theme again is the system is actually somehow a Hilbert scheme of points on a surface in an interesting way, and it ties in with very classical integrations of these systems in places when you've got explicit coordinates, and but also to some interesting ideas. And we're going to see how that generalizes. So just to recall, what did we have for the Hitchin system? We had a rank n moduli space of pairs, E phi, where E was a rank n holomorphic bundle and phi was a Higgs field. So it's a section of the endomorphisms of E tensor the canonical bundle. From these, we had two invariants. The first is a spectral curve, which is living in the total space of the canonical bundle. And it was cut out just by taking the spectrum. So the determinant of phi minus z times the identity equals 0. The other item, the other piece of data is a quotient sheaf. So you take the co-kernel of phi minus z times the identity, and of course, away from the spectral curve, it's an isomorphism, so there's nothing there. And so you get a sheaf that's supported on the spectral curve, and it's generically a line bundle, basically, when the curve is smooth and has this, you know, multiplicity 1, you're getting a line bundle. And there's this sort of abelianization that occurs repeatedly in this setup. And wait a minute, I'm going to try to, oh dear. No, that's not what I wanted to do. Excuse me. This is what I wanted to do. So it occurs repeatedly where your bundle gets replaced by a line bundle, and but on a bigger curve. And so the point was that you could sort of shift things. And I'll say a bit more about that later. So you're representing essentially by a unique divisor on sigma. And this, the key point is that symplectically, the moduli space becomes the Hilbert scheme of points on this surface. Now it's a sort of semi-local thing. It's only on the neighborhood, say, of the Jacobian of one spectral curve, so a family of Jacobians. And the reason basically is this normalization to a divisor. So that's a bit of a subtlety. We had some other examples, Skleanin system, so that I worked on with A.L. Markman many years ago. So now you can just take your curves to be either elliptic curves or rational curves. And the endomorphisms get replaced by automorphisms. And again, you get a spectral curve and a line bundle as before. And this time your surface is no longer the conical bundle, but it's the product of P1 cross X. And but this time there's these manifolds or Poisson. The symplectic leaves basically are given by the fixing the intersection of the spectral curve with 0 and infinity in P1. So it's different symplectic structure, and we studied these last time. And but it's still, you have this relationship to a surface, and again it's semi-local in the sense of on a neighborhood of a Jacobian in the fibration in the integrable system. A bit of a curiosity was that you could also define a deformed Hitchin system. So we saw that there was a classification of Poisson surfaces, and there were abelian varieties and K3s, and we put those aside, and the rest were essentially ruled surfaces. And of a rather limited variety, and the Hitchin and the Skleanin systems basically sort of ate up most of the systems. But there's this orphan, and it's a rather interesting one. You have a basically a bundle of one jets. Take a line bundle, and you do this, and it gives you a non-trivial extension with this kernel of V is a canonical bundle. So you're getting the thing. And what you do is you replace the endomorphisms of E by you take the identity here, and you take the sort of affine line above it, and basically from that you can define maps that under this V to O map go to the identity if you take endomorphisms of E tensor V. And these are sort of connection-like objects, but they're only connections on a line bundle W, and so you can still define a spectrum, and you still get line bundles, the co-kernels again, and what you're getting is basically a deformation of the Hitchin system. And again, it gets represented as the Ajit symmetric product. Okay, as I was saying, all of these isomorphisms are semi-local. So they're in the neighborhood of a fixed Jacobian. So your picture is an integrable system. You've got a family here of Jacobians and curves. And so somehow in the neighborhood of some open set of Hamiltonians in the base, you can define this. The global structure is more complicated. It works better, of course, when the degrees are just right, in which case you get something at least for all the smooth curves in the locus. Okay. So I'd like to sort of just pause for a moment and study the global, the local geometry rather of these systems. So I'm just going to suppose what I've got is a local system of an integrable system of Jacobians. So this is a G-dimensional space. You've got a 2G dimensional space, and the fibers are Jacobians of curves. So genus G curves. So the fiber is an abelian variety, and the base is just, say, a ball. So corresponding to this, there'll be a family of curves, which the global space is G plus one dimensional, and now the fibers are just one dimensional. Okay, now you want this thing to be an integrable system, and if you sort of write out what you can do, well, you can do the thing you have for real integrable systems. You can go to action angle coordinates. But now there's a little bit of a twist, which is that for you've got G dimensions, but instead of G periods, as you would have for real tori, you have 2G periods. And so basically what action angle coordinates do is if you want, normalize the periods to just a standard well, basically to some fixed number. So what you can do here is just normalize half of the periods, so that, you know, the usual A periods of a Riemann surface. So as I say, you normalize the A periods to 1, the B periods are still sort of left floating, and then the symplectic form takes a standard form. And it's a nice result, and there's a much more sort of sophisticated version due to Donaghy and Markman, but the sort of basic version is that the B periods that remain will be have to be a second derivative, so a Hessian of a function. Basically, this is just so that when you translate by the B periods, the form gives the same value. Okay. Now, suppose you have that. Well, what have you got? Well, you've got, because it's a family of curves, you've got a family of curves, you've got an Abel map. So let's sort of try to draw this a little bit here. So here's U. Here's the Jacobian of sigma. Here's U again. And now you've got, this is, the fiber is G-dimensional, the base is G-dimensional, base is G-dimensional. Here the fibers are one-dimensional, so here's just sigma. And what you have is the Abel map, so Abel of P, just choose a normalized basis of holomorphic differentials, and you can map the Riemann surface into its Jacobian. Okay, so you have a map here, this G plus one dimensional space, right, into this 2G dimensional space. Okay, so what can happen? Well, the form, if you pull back, I used I here instead of A. Sorry. Sorry. Okay, so you've got this map I. You can pull back the form, and again, notice they're full of base point choices here. So it's a bit. But suppose you're lucky, and the form is of minimal rank. So that this form, which is, you know, it's a symplectic form, so its Gth power is non-zero, but its pullback doesn't have to be like that. And so suppose this is minimal rank. It can't actually vanish, and that's just a consequence of the fact that there's always a differential form on a curve that's non-zero at a point. But it can have minimal rank, and suppose it's uniformly minimal. And so what this means basically is, and it's a theorem that goes back to Darboux, that the I star of omega is just, well, du wedge dv for some form locally. Okay, in slightly more elaborate terms, under this embedding, the variety is coisotropic, and you can quotient by null foliation. And so what you get, just because you've got two coordinates here, u and v, is you get a quotient surface into which this form I star of omega projects, and you get a symplectic form omega on q. So the curves all embed in q, and again, that's just a feature of the fact that there's always a non-zero differential form at a point. So you want to think of a projection projecting out, and you're getting some sort of surface q here. And these curves, these spectral curves, all embed, but now, of course, they sort of embed, and they all sort of get, they're not all lined up nicely as in the fibration S here, but they're embedded, and they have normal bundle. That's the canonical bundle, because Q is a symplectic surface. Excuse me, I'm going to kill this telephone. Okay, so that's a picture. So there's this surface Q. Now, what you can again show is that for genus high enough, if you had two of these Abel maps, both giving the same result, then in fact the Q only you get the same result basically. The pullback of the forms are the same, and so the Q only depends on the family of curves. And just a sort of obvious remark, when G is equal to 2, you're in 3 dimensions, and so there's no room for a 4 form. So back to normal. Okay, and what's more is that you can then define basically a sort of birational map between the Hilbert scheme of points on Q and this family of Jacobians. And the way you do it is so here's your family of Jacobians. So it's living over U. And then you've got your family of curves. And it's living over U. And what you do is, instead of taking, you'll take the fiber-wise symmetric product. So it's the Hilbert scheme of points for a curve, but say just call it explicitly. So this is the fiber-wise G symmetric product. So here, this is G-dimensional. This is G-dimensional. And again, because the Abel map is basically, additive, you'll get the Abel map here into the family of Jacobians. And so you're getting basically generic isomorphisms both ways. And well, I mean, this is the way you often can think about a birational map, right? There's something above it of the same dimension that's mapping to the generically one-to-one to both pieces. Okay, so you're getting, in other words, just out of this local geometry, a Hilbert scheme. And you can turn this around. So you're getting a symplectic surface Q and a smooth curve S in Q. So you're just taking your symplectic surface and smooth curve, and then because the canonical bundle of the surface is trivial, then sections of the normal bundle on the curve correspond to differential forms. The deformations will give a family of curves. Oh dear, this came out badly, sorry. S over U. And you'll get fiber-wise symmetric product, and then to the Jacobian. So you can sort of flip this around. So you're seeing basically the surface is an invariant of the system. And again, I'd like to emphasize it's not quite complete. Oh, damn. So I'd like to sort of pursue this lecture by talking about what happens in other cases. What's the analogous creature for this surface system? So just to emphasize, there are some cases where these things occur. So you can get the Hitchin integrable system, and you can get it for arbitrary groups, basically. So you've got a pair consisting of principal bundle, and then a section of the adjoint bundle tends to the canonical bundle. And then there's a stability condition. And you're going to get a moduli space M sub G of X. You'll again have commuting Hamiltonians because you take basically all the invariant polynomials on the Lie algebra, and you apply them to the Higgs field. And you'll get forms which you can then decompose into components. And it's a computation of I think, Hitchin that shows that these give you an integrable system. In other words, there are lots of them, and there's just enough. So what's the geometry that occurs here? So let's go back to GLN. Sorry, this should be phi. So instead of an individual eigenvalues of phi, I want you to think instead of all the ordered sequences of eigenvalues. Okay, it's basically the same data. But so I'm going to ask you to think, in other words, of all possible diagonalizations of phi. Okay, this gives you n factorial points in C to the n, and the family is invariant under the action of the symmetric group. Okay, so the symmetric group is the Vial group for GLN, so that's interesting. So I want you to think for general G and generic phi, think of generic X, of all possible conjugations of phi to the Cartan subalgebra. So you'll be seeing a Vial group's worth of points in general. So I've sort of drawn them here for 1 point, right? And you're getting a Vial orbit. So this is the case of, I suppose, SL3. You're getting a Vial orbit, and of course, you're getting then as you move in the base, you're going to be getting a curve over the base. And you see that the branch points are actually of this curve are really quite constrained. They only occur basically when you hit the walls of the Vial chamber. At which point, and they're still a Vial orbit, but the size of the orbit is decreased. So you get this invariant curve, and it's Vial invariant. Okay. So the analog of the line bundle. Well, the bundle lifted to the spectral curve comes with a natural reduction to the Borel-Vial group, the stabilizer, basically, of that form. And so you can take this Borel and you can project to the Cartan subgroup. So just think of transition functions. If I have transition functions for a bundle with values in a Borel, I can project from the Borel to the Cartan and get an H bundle. It's not invariant, but there's a twist, and it's computable in terms of roots and branch points and things. This is Donaghy and Skonyamila. And just let's take the result to be normalized to degree 0 and call the result pH. Okay. So now you've got something that is invariant. It's an H bundle that's invariant. And well, H is an abelian group, so you're basically thinking of the Picard variety or the Jacobian. And note the action of W intertwines the action of H and the action on the curve. So it's this complicated thing. What are H bundles? Well, H is C star to the R, basically. So you're getting basically R line bundles. So a more elaborate way of writing this is to take the quotient over Z of the tensor product over Z with the lattice of the. Okay, so the integer lattice in the Cartan subalgebra, and so you're getting quotients, and these are known as generalized Prim varieties. Okay, so you've got this system, and you could say, well, what's the equivalent of the surface here? And there doesn't seem to be any around, and then you just do a bit of linear algebra, basically. But you do have the abelianization. So for smooth spectral curves, you get this sort of, again, result that gives you a correspondence. And I'm shoving these twists and such to get to P sub H under the carpet here. But basically, you're getting that the data, at least generically, of sigma and pH are the same. And so, so then what's the geometric picture is that you've got a family of Prim varieties over a base, U, and this is, everything is W invariant, right? So you've got a, sorry, these are on the base, it's, excuse me. On the base, the action is trivial, sorry. So it's a family of curves, but it's, the action is the, so, but you've got a action on the fibers of W. Okay. Oh, sorry, these are invariant too. Sorry, I'm getting ahead of myself. Okay, the geometry then of fibration of family of Prim varieties, and W acts trivially on this whole picture, so my apologies. Okay. So, I don't know, let's call this PR. Okay. And the Hitchin Hamiltonians will give you linear flows on this thing. So that's the, so what would the Darboux coordinates? And again, this is things I did a while ago with Eyal Markman. Well, first of all, you can abelianize. So deforming the H bundle, it's going to give you an invariant sort of set inside the H1. So it's deforming the line bundles, basically. And deforming the curves will give you an equivariant section of the normal bundle. And so, but your normal bundle is just the, it's sitting inside this canonical bundle tensored with the Cartan. And so again, with some splittings that you can make fairly geometric. Oh. I just be launching it directly and see what happens. Does it work? No, it doesn't. Oh, it does. Goody. Okay. So with a remember, you're getting here the canonical bundle. And so it's basically the Serre duality pairing and sort of jazzed up with the Kaplan. I'm probably forgetting a star here because it should be an H and an H star. Okay, so the way to think of it is as follows. Well, first of all, there's an equivalence between, you're taking this Serre duality pairing here between two invariant pieces. And so the form you get is invariant. And now you can also think of the invariant forms where you're allowing the line bundle to be general. And that's the reason for that is basically it's just Schur's lemma. If you want invariance, and you're doing it between the two invariant pieces above, if you're adding in extra pieces here, nothing's going to live there if you want invariance. And now you can just do a little bit of linear algebra. And I forgot something here, which is probably putting an H star here. So this is the sort of key bit, which instead of living on the H bundles, you now on the line bundles, and you sort of brought out the H star, and that's just linear algebra, basically. Okay. So our symplectic form on the family of prims becomes an H star valued symplectic form on the family of Jacobians. And now you can pull this back to the family of curves embedded in this thing via the Abel map. And you notice that this bundle has a natural invariant H star value 2 form. So this is where you get into business. And so what you're getting is the pullback of this H valued form under the Abel map is just this geometric form on the variety, and the variety is not, if you notice, it's sort of the rank of the group plus 1 dimensional thing over the base, which is X. Okay. Now you can play this game as for the Hitchin system by adding in a divisor and allowing poles. So you get a Poisson moduli space. The symplectic leaves fix the conjugacy class. And instead of thinking of the Poisson space, maybe just think of it as a log symplectic form. So because they're simple poles. So you can just think of it this way on the bundle. And the Hitchin Hamiltonians, again, are given by invariant polynomials. The Casimirs, so the functions that are whose Poisson brackets with everything are just the values of these polynomials over D. And again, you get a natural invariant H star log symplectic form. Oh, I've said this twice, haven't I? And again, the Abel map gives you these Darboux coordinates. Another example that's kind of interesting is you can do, again, this Sklianin trick. So on an elliptic curve, so it works in elliptic curves and rational curves, basically, again. You can define a Sklianin bracket for arbitrary groups. And actually, I think I've forgotten Varchenko here. So this is using computationally the dynamical R matrices of Ettinghoff and Varchenko. Geometrically, what it means is that the generic bundles of degree 0 on an elliptic curve reduce to the torus. And this is only generic, and there's when they don't reduce to the torus, it's basically, it behaves roughly in the same way that Jordan forms do. So there's there's some non-trivial extensions, but there's a sort of torus piece that's there anyway. And so you'll get a space of pairs, a principal bundle, and a meromorphic section of the automorphisms. Now, what will the symplectic leaves look like? It's kind of interesting. It's basically a theorem of Iwahori that gets used. Recall the SLN moduli space. The symplectic leaves were given as follows, that you fix the polar type of the singularity. So that you're a point given by, say, a coordinate x equals 0, where x equals 0 is the point you're interested in. It's where the singularity occurs. You're given basically the sort of polar behavior of the matrices. Now, when I say pole, it includes zeros. So these m's here can be either positive or negative. Some of them can be 0. And you can, the sort of action you're considering is basically pre and post multiplying by things that are holomorphic, but invertible. And so this sort of orbit of these things fixes the type of the singularities. And the general group's done in the same way. You fix the locus of the singularities. And each point of these, you fix a co-character. And you can see basically this is a co-character for the the diagonal group. And so you get some data that location of the points and a multiplicity, except it's a multi-multiplicity here, because it's several points, several integers. And rather similar to a divisor. Well, with that, you'll get a symplectic space. You'll get the Hitchin Hamiltonians. Again, the Casimirs now are the locations of the singularities, so it's different from the Hitchin system. You'll have an invariant spectral curve, and again, you can build invariant forms with poles now along 0 and infinity, and the pullback via the Abel map again gives homage. So it's a similar geometry. So now what's the local picture? We had this local picture that gave us, with this rank 2 condition of minimal, if you want a system of minimal complexity, gave us a surface from an integral system of Jacobians. So here we have a system of Prim varieties, and what can we do? Well, take a family of invariant curves, U, and now again an integral system of Prim varieties over the U with a symplectic form. Okay, and it's a Lagrangian fibration over U. One remark here is that the W doesn't have to be a Vial group. So this works as well for the classical Prim varieties, where the omega is W is the integers mod 2, and the representation you're choosing, sort of an integer representation, is just the sign representation. So 1 acts by 1, -1 by -1. And so you're looking at curves with an involution. So that works there too. So again, you've got these you turn your lattice into a vector space, V, and then you'll get a V star valued form, WG. And again, you can embed the family of spectral curves into the Jacobian via the Abel map. Now I've called it A. Excuse me, A star. Oh dear. So maybe just A. And now the system's of rank 2, if basically it's the wedge product. Now this is a devalued form. So basically it's just saying you want all the components to wedge together to 0. So it's, again, a system of sort of minimal complexity in terms of the Abel map. And under some very, fairly reasonable genericity assumptions, from this family, quotienting by the sort of joint null foliation, you can basically reproduce this, this geometry. So you're going to get an R+1, just as for the Hitchin systems. You're going to get an R+1 dimensional variety. And your spectral curves are going to embed in this thing, just sort of reproducing the sort of picture that I had. And there's going to be an action of the Vial group on this R+1 dimensional thing. What's surprising is that there's enough invariance here so that there is a foliation by codimension 1 varieties. Okay, remember our system for the Hitchin system had this projection to the base curve. You had k of x tensored the captain, and it projected to the base curve. So the fibers of that are r-dimensional. And the interesting thing is, under this system now, there's the same story. And you're getting basically a curve for free. You're getting the base curve, which is now called sigma. And so your Vial quotients of your curves SU are all sigma. So the difference in this Vial invariant setup is that the curves they all have a simultaneous quotient. I mean, they're Vial invariant, so there is a quotient, but the quotient's always the same. And so you're not only rebuilding the geometry of a surface, but you're building, well, here it's an R+1 dimensional variety, but you're building the projection. And the constraints on these genericity are actually quite mild, so it's a bit of a surprise. And basically was Markman's insight. So now I'd like to close with a rather pretty example where it's no longer sort of spectral invariants that do the work for you, but rather the K3, the geometry of bundles on elliptic curves. So this is due to Ron Donaghy, and I suppose I should apologize for getting essential details wrong. What you've got now is you're taking a K3 surface over P1 with elliptic fibers. So I said in my surface example that the K3s were just sort of sitting there and they didn't seem to correspond to much. So here's an example where it's still a K3, but there's some interesting stuff going on. So your K3 surface, Y over P1 with elliptic fibers. Okay. So your picture, here's P1. So fibration, elliptic curves. So this is sort of mixed real and complex picture. And on each elliptic curve, basically, you can restrict a bundle on an elliptic curve. And if they're of degree 0, as I was saying, they generically give you sum of line bundles. And so if you want on the dual elliptic curve, you're getting a sum of points. Now, as you're varying your curve, you're going to get your elliptic curve. You're going to get a sort of spectral curve that's living above here. Now, the key thing, of course, is that it's a G bundle, and so there's a Vial Groups way of doing this that's important. And so basically, you're not just getting, this is only a local picture, and more invariantly, you're getting a Vial orbit in this picture. And so you get a curve in the fiber product over P1, which replaces the Ez with Ez star tensor the chi. So this is the sort of R+1 fold. You're going to get, in addition, an element of the Prim over the spectral curve, and you'll get an integrable system of Prim varieties. So roughly speaking, the curve tells you what the bundle is over each E sub z. And the Prim element, which is this sort of line bundle, tells you how they fit together holomorphically. So if you just had the curve, you just know what it was on each elliptic curve. The bundle was on each elliptic curve, but you would have the essential sort of global information for fitting them together wouldn't be there. So it's an interesting example because it's not given by a sort of spectral construction, but by a Fourier-Mukai transform. So it's a sort of spectral decomposition of the bundle by twisting with line bundles that will pick this out. And of course, it's a thing that's relative over P1. And it's another example of these rank 2 systems. So they do occur elsewhere, but again, it's fairly fairly tight. Now these rank 2 systems, it's not necessarily rank 2. So it's these sort of rank 2 systems are somehow systems of minimal complexity. But the nice thing is they do sort of coincide with interesting geometric examples. And so, yes, the slides have disappeared because I've given up. And anyway, I'm done. So I'd like to thank you for your patience, both with technology and with the speaker. And I think I'll just stop there.
Thank you very much for a lovely talk and a lovely series of talk. Does anyone have any questions? You're welcome to post in the chat or raise your hand. Well, I think you should. Oh yeah, Aswin, go ahead.
Yeah, hi. Yeah, thank you for the wonderful series of lectures. So I had a question about this construction called separation of variables.
Yes.
How much is known for arbitrary Hitchin systems, like for arbitrary group G?
You mean which the quantum one or the?
Both. I mean, I only know the literature for SLN, so I would love to know anything for arbitrary G.
Yeah. Let's see now. How would you do that? You'd probably try to find. You'd use this surface theorem, and it's not. You see, it's sort of getting you almost there, but you could express your either taking averages over the Darboux coordinates. You could probably. I was thinking about it a bit last night. Actually, you could probably take these sort of curved coordinates and average them, and then take sort of abelian integrals that are averaged, and so Vial invariant, and that would be your linear coordinates for the flows. And then I must admit the actual sort of technology for the equivalence of this sort of standard 19th century trick for producing the dual coordinates. It's probably there, but I must admit I'm a little bit. It would have to be sort of rethought or maybe thought out for the first time. Yeah, so there's a bit of a lacuna there. So my apologies.
Thanks.